let us come back and start your 2012 paper. So in 2012 paper, again we have 3 questions. Let us solve those. So what do they give us? First one, explain the following observations giving an appropriate reason for each. Okay, account for the following, give reasons, find the reason. Such questions are quite common in D block and P block. So let us see this. The enthalpies of atomization of transition metals are quite high. Okay, this I've done one video based on enthalpies of atomization, giving you certain questions and trends also. So I've numbered that in the playlist as video number 12. Please watch that video. You'll have a clear idea of enthalpy of atomization. Done. So again the same question. There occurs much more frequent metal-metal bonding in compounds of heavy transition elements. Otherwise, how was this question asked? Why does transition metal exhibit variable oxidation state? It is the same question, right? So how should I write this answer? So when I have to write this answer, just important thing is 3 particular keywords. First important thing, as we know, transition metals, they when I see your 4D series, they are what do you say? You have lanthanum adjacent to your zirconium and hafnium. Because of that, they experience a concept called lanthanide contraction. So what is that concept? Basically, that is dependent on your ionic radii. That is what lanthanum to lutetium. So most important thing, they're going to form metal-metal bonding only or based on ionic radii. And that lanthanide contraction, which is acting on them, it has made the ionic radii less. So that is first important concept for stronger metal bonding. Now, so this one ionic radii, okay, small. Next important thing, you have participation of n-1d electron. That's why it's going to give every time 1 electron after the other. It's going to give you 4s2 electrons, and 3d it can go till 10 electrons, isn't it? So what is the next concept which is affecting the stronger metal bonding? That is variable oxidation state. That is participation of n-1d electrons. So because of this, it's going to form a strong metal-metal bonding. See here, there occurs much more frequent metal bonding. It's going to hold because the 3d electrons are closer to the nucleus. The effective nuclear charge is more, and when it tries to form a bond with the other element, it's going to form a compact and packed tight structure, metal-metal bonding. Done. So next important, why is this again having a stronger metal bonding? Yes, because of variable oxidation state, they form complexes. So we already discussed, when it's trying to form a complex, what type of bond is it forming? Coordinate covalent bond. Again the bond is strong. So these 3 reasons make the metal-metal bonding very high or strong in transition elements. Smaller radii, yes. Variable oxidation state, yes. Forming complex, yes. All these make the metal bonding strong. Yes. Next one. Mn+2 is more resistant than Fe+2 towards oxidation. Okay, very nice question. So Mn+2. So when such thing is given to you, first try to write the configuration. Manganese is 3d5 4s2. Fe is 26 atomic number, 3d6 4s2. Now what happens when I have to write Mn+2? This becomes 0. Now when you are trying to, now this is which configuration? This is your stable configuration, stable half-filled configuration. Now this stable half-filled configuration, when you are trying to lose electron, oxidation is loss of electron. So where will you take out electron? You have to take out electron from here. So when you are trying to take out 1 electron from here, this process is called oxidation. What will the configuration change to? 3d4. This is stable configuration. This is unstable. So now tell me, will manganese prefer showing oxidation? No, isn't it? Yes. So first reason, what reason are you giving? Manganese, yes, it is 3d5 configuration, point number 1. When it has lost 1 electron, it's gone to 3d4, it is unstable. So because of this unstable configuration, yes, this is not going to prefer oxidation. Once again, yes, simple terms. If you still want to write, let us make it easy and neat and write. So let us see. Mn+2 gets converted from 3d5 to 3d4, which makes it unstable. Hence is resistant to oxidation. Done. Let us write, come back to Fe. Now they say Fe plus 2 is fine towards oxidation itself. Why? When I have to take out Fe plus 2 electrons, this becomes 0. Okay. Now 3d6, I have to further oxidize it, means loss of electron. So from here I am going to subtract 1 electron. When I am subtracting, this becomes 3d5. Now see, this has become stable. Now what is happening here? Iron, because of oxidation, it has lost an electron and it is in stable configuration. 3d6 to 3d5, stable. That is why Fe plus 2 prefers oxidation. So the concept is, this is resistant to oxidation, it prefers towards oxidation because of their configurations. 5 to 4, 6 to 5.